Hello, everyone. Welcome to the webinar series toward open data lakehouse architecture. And today, Marek Wiwiórka, who you already know because he presented our first episode, will be talking also Tomasz Kostyrka. So I believe this episode will be even better. And today, Tomasz and Marek will be presenting to us data lakehouse storage layer. So I will give the voice to them. And yeah. Very interested about it.
Thanks.
Thank you. Okay, hello everyone. Once again, let's maybe start with some general introduction to the topics of our season first of Open Data Lakehouse series. In general, this series of webinars is about, as the name suggests, the Open Lake Lakehouse architecture, and in particular, we would like to discuss technological landscape, both of proprietary and open source tools. What is the business impact of Open Data Lakehouse architecture to your organization? Some experience from our previous projects will be also shared to shed some light on project organization. The topic that will appear during each episode of our series will be, of course, cost optimization. And last but not least, we will also introduce you to the emerging trends and some new technologies and some new ways of implementing open data lakehouse architectures. Over the series, we would like to share both some theoretical knowledge, introduce you to the core concept, as well as some real life scenario and examples of past projects. We combine the theory and practical examples, and last but not least, we will also try to prove the effectiveness of some technologies over the others and approaches over the others, showing you some benchmarks. Today, as Xebia already mentioned, we are going to discuss the storage layer. Could you maybe turn? Yeah. But before we go into the details, let's maybe recap of the first episode. During the first episode number 1, we deconstructed the data lakehouse architectures. What are the main building blocks? We discussed of course, from the higher perspective, the compute, metadata, and storage ecosystems, and already shared some market trends. Today, we are going to zoom in on the storage layer, and in particular, we are going to discuss the open table formats, open file formats, show you some performance tuning tips, and we will conclude with a short demo. Tomek?
Okay, thanks. So as Marek said, let's start with open file formats. And before we dive deeper, let's maybe define what do we mean by big data open file formats. Probably all of you know formats like CSVs, XMLs, JSONs. I hope lots of us also know what Parquet or Avro is. And by big data formats, we mentioned mainly Parquet, Org, and Avro. CSV and JSON files are not useful when processing terabytes of data, especially in the bulk way. And this is because they miss few of the let's say functionalities, because file formats are not only containers for the data. It's not the only requirement we have to store the data. In big data workloads, we want a little bit more. For example, we would like to have a schema, a metadata into our files so that we don't need to guess or define them externally. We want to have good compression capabilities, and those formats should be prepared for that. And we would like to have formats that are ready for some optimizations, techniques, and features that we're gonna present later in this webinar. When we talk about the big data formats, it's also important to understand what columnar versus row-oriented formats are and how they differ. At the first image of this slide, you can see a standard row-oriented file format that could be, for example, a CSV file that we all know, a format in which the data is stored in the same order as the rows are stored. So row number 1, row number 2, row number 3. It's a really good format when we want to append it, when we want to pull a small amount of the data and we need to pull the full rows, not, for example, whole columns of our table. But it's not effective in most of our big data analytical workloads. The columnar format, on the other hand, that's presented below, assumes that the data is stored physically on a storage in a different way. By different, I mean that the data is stored by columns. As you can see in the colored image at the bottom, the data is reorganized, and for example, the first column with the name is stored as a consecutive block of data. That brings us some new possibilities when analyzing the data, especially when we want to load the data from the storage. It allows us, for example, to load separately the columns and skip a lot of the parts of our file that are not required in our processing workloads. For example, columns that are skipped by our query. The best example of a columnar format, I believe the most widely known, is the Apache Parquet file format. That we would like to dip a little bit deeper to explain the concepts and maybe show some examples on how this columnar level format really supports our workloads and how they speed up the performance. If you look at the Apache Parquet internals, you'll see that it's a little bit more complicated than CSV file where you just see the rows saved as a consecutive lines of tasks. Parquet format is internally composed of row groups, so containers for buckets of rows that are then split into column segments, and those column segments are split into the pages. Those column segments are saved on a disk in this columnar fashion, and the pages are segments, the smallest segments that can be read from the disk. At the end of the Parquet file format, after those rows, groups, and whole column segments, we have a file metadata footer that contains statistics of those row groups columns. So for example, minimum, maximum values, the ranges, the data types, etc. Which, as I've said, are self-contained, so allow us to query the data without external systems describing the data types or guessing them based on sample values from our columns. Okay, but what benefits do we get from that? The first benefit, I think most important, is the possibility of doing a projection pushdown. Projection pushdown is a situation where we know that only some of the columns will be required in our query, and we don't load the rest in our process. So for example, in this sample query, you see select average from column A. We already know that only the column A is required. And because of the columnar way of saving the data on the disk, we can only upload the data related with column A. Because of the file metadata, we can easily reach the data on the disk. We don't need to upload everything, decompress it, and then just skip 90% of the data. We pull only what is required, and then this extremely speed up the part of our processing time responsible for loading the data. But that's not all. That was just the first level. The second one is called row group pruning. Also in the file metadata, we have a statistics about all of the columns in our row groups. For example, the mix and minimum and maximum values. And looking at the second query, we can see that only those rows with columns smaller than 150 are required in our query. And based on the metadata about row group 3, we already know that this row group can be fully skipped because none of the rows inside will fit our query. Combining Combined with projection pushdown, you see that we can limit the data loaded vertically, horizontally, and extremely reduce the number of rows that are even pulled from the disk. The third one, if we try to even go deeper, is called a directory pushdown. That's related with encoding. That's also important. It's not yet the encoding and compression are two different things. Encoding is done faster and before the compression part. And if you look at our example, you can see that some of the columns might have small or medium-sized cardinality, like the one from example with countries. In that situation, in Parquet format, we can optionally create dictionary pages with codes for each of possible unique keys that we can find in the columns. The first benefit is that instead of multiple long strings, we reduce this to just small integers. Like you can see from page Poland, we go to consecutive zeros, which reduces the file size. But besides of that, we get this dictionary that contains all the possible elements we would find in the row group. And reducing the storage size is the first benefit, but the second one is that during the query, we can look at the dictionary page and see all the unique values that we can find in the row group. So if you add a query with a where clause that requires only our rows with Poland as the country, by using the dictionary, you can already know that the row group one will be skipped. So let's say it's also something like a row group pruning, but for columns with low cardinality where range is not enough, and we can more specifically reduce the number of rows. Okay, last one, also optional, that's called page pruning. In some cases, in Parquet files, we can find statistics even on a page level, not the column level. If those would be found in the file, and if our compute engine knows how to read them, we can even load the data on a single page level, not a row group level, and reduce the number of rows pulled even more to the size of a single page. But as I've said, this mechanism is optional, and not all of the compute engines are prepared to work with it. Okay, those are the prunings. So all the mechanisms that allow us just to skip loading of the full file. But on top of that, we have also compression mechanisms. And because of the fact that our Parquet file is split into those column chunks, the compression is extremely more effective than when compared to files like JSON, XML, or CSVs. Data in Parquet format is compressed on the level of a single page. That should be the same data type, and if data is properly sorted, it should also be quite similar to each other. This kind of pages are compressed more effectively than just random rows of data where you can find everything from integers to strings or Boolean data. We have multiple ways of compressing the data. In most of the engines, snappy compression is the default one, but depending on our workload, if it's more real-time analytics workload or batch processing workload, we can decide to switch this to a different compression type. There's no one gold standard that's always the best. Treat snappy as a default, and if you want to change it to something else, you need to probably just test your workloads and see which one performs the best. And all those things I've mentioned here are not possible in the classical file formats, and that's why when working with Apache Parquet, you can see those enormous time reductions in your queries. So if you hear that something suddenly started to work 20, 30 times faster, then yes, this is possible when you take into consideration all those mechanisms and properly prepared tables in Parquet format. Okay, that's Parquet is not the only file format we'd like to mention. Let's now jump to Apache Avro. So Marek, if you can say a few.
Sure.
Words about it.
So Apache Parquet is especially efficient while running analytical queries over it, but it's not the only type of workload that you can find in the big data ecosystem. For example, in the streaming scenarios, there are some there are in fact other requirements, and other things really matter. This is why the community came up with another specialized format, which is called Avro, and is also available under Apache license. So this is also a binary format, but as I mentioned already, it's designed for efficient exchange of various type of messages using different kind of queuing systems, like, for example, Kafka or some managed services in the cloud. Unlike Parquet, it is a row-based realization format. It's rather optimized for transmission and compact representation than for running analytical queries over it. Of course, it's possible, but it's not recommended as storage format for long-term storage and for analytical purposes. Similar to Apache Parquet, it's also schema-based. So schema is always attached to Avro files. It can be directly attached as a kind of additional element of a file, or it can be referenced using a unique identifier from a system called schema registry, which is in many cases default component of streaming systems. It also supports schema evolution. This is why it's possible to store messages of different schema within one file and query them or process them together. It of course is supported by a great range of programming languages, mostly popular in a, as I said, open source streaming system powered by Apache Kafka. It also integrates with very nicely with RPC systems, so remote procedure call systems and data pipelines when we need to exchange data between system over network. Another specialized table and file format is called Lens. It's also to some extent inspired by Apache Parquet, but it's optimized for ML and AI type of workloads. Following Apache Parquet principles, it's also columnar format, but it's rather optimized not for like scanning large amount of data, but rather for random access type of work. So when you need to quickly query your data set for some values, filtering out some unnecessary values. It also have yet another distinguishing feature of Lens is that it have a built-in support for multimodal type of data. So it also has support for images, for audio, and it also can store large-scale embedding vectors that can be used for building various search systems based on semantic type of search. It also supports zero-copy schema evolution and partitioning, and it also capable of exposing APIs for hybrid, so semantic and keyword search. So this is why Lens become the default format for LensDB vector system that is very popular among open source AI initiatives. It also has regular database system. It also has support for various kinds of secondary indexes. to speed up the point lookups even more. And already it has been started in discussion to include Lens as one of the available file formats for Iceberg table integration. So far, we discussed storage formats that are meant for keeping data at rest. But if you would like to efficiently exchange data between processes in memory, there is yet another solution for that. It's called Apache Arrow. So the idea behind this file format, which is also a columnar one, is to standardize the format of data exchange between different applications, so that if you are processing data in memory, you don't need to pay additional penalty of serializing and deserializing your data. It's particularly popular if you are implementing any kind of integration between heterogeneous systems written in different programming languages, like, for example, Rust and Python, or Java and C++. If you would like to efficiently exchange data without any penalty, which is called zero-copy data exchange mechanism, Apache Arrow is the right way to go. It also has a great support for different programming languages, as I said, and because it has a standardized memory layout that is columnar and optimized for vectorized processing, it's very often file format, memory format of choice when implementing high-performance execution or query engines. Okay, so maybe to wrap up what we discussed so far when it comes to querying file formats, especially file formats like Apache Parquet, so columnar and meant and designed for analytical purposes. So the flow from left to the right hand looks like this, that we are first of all, of course, opening a file. We need to read or load the Parquet metadata in order to learn more about the file layout and some additional statistics. Then if we start processing queries, we first starting the query projection optimization. So by doing so, we are able to filter out unnecessary columns and later on, of course, row groups and pages. Pruning by predicates, or predicate pushdown mechanism. By doing so, we are also capable of filtering out fragments of files using the optimization of the row group, or even some more sophisticated mechanism, like, for example, Bloom filters. Finally, as Tomek mentioned, it's also possible to go even deeper and use mechanisms of pruning at the page level. But many popular query engines, including Apache Spark, have not yet adopted this mechanism. But for example, Apache Data Fusion is one of the engines that is capable of page level pruning. So this is how the query is processed. But if you take a look at what's happening in the memory, so we are starting from the Parquet file stored on some external storage. Then we got the memory mapping of the Parquet file and starting the file decoding. And finally, once all the steps that I just explained, so the one from the left to the right hand, are accomplished, we in many cases, for example, in case of Apache Data Fusion, we end up with a set of Arrow record batches that can be later on processed in memory by heterogeneous systems.
Okay, thanks, Marek. So now we know what the file formats used in big data workloads are, how they work. we can move to them. But if we move our data from the old style data warehouses to our new data lakes based on those open, cheap, and performant file formats, we'll lose few of the functionalities that we are quite used to, and that solved some of the problems that appeared in the data warehousing world. For example, if moving to tables based on those pure file formats, we'll probably use the ACID compliance. So we will lose all the mechanisms that that guarantee the isolation and the possible work of multiple users at the same time. And we'll also might hit into few performance issues related with the metadata read and file listing. For example, as mentioned, Parquet formats have the metadata inside of them at the footers, which means that you always need to load the metadata part and read it to understand what's inside. And for some big tables with tens of thousands of files stored on cloud object storage, the file listing might also start to become a problem, because if you want to read the table and each time you need to list all of the files in a folder, then read the metadata from end of them, even a simple query might start to take too long. And to solve this problem, few new mechanisms or concepts were proposed, and we call them the open table formats. By open table formats, we most of the time mean the most important three on the market. So Apache Hudi, Delta Lake, and Apache Iceberg. There are different ones like Apache Payment that we'll probably mention during the webinar on streaming. But for now, let's focus on those core three. And let's look at the details here of the data lake format to understand what was added and what is solving the problems we faced when moving to pure file formats. As you can see on the diagram, the data in our tables is still stored in the Parquet files. Here on the diagram called from F1 to Fn, those are just files with data. But on top of that, a log layer is added. A log is just a simple folder with multiple JSON or Parquet or Avro files, depending on the technology, that describes the tables, keeps the statistics, keeps the information about the versions of the table, keeps the information of which files are part of the table at the particular moment. And this concept of a log file solves those three mentioned problems. We don't need to do the full file listing because the log file keeps the information about the files containing the data of our table. We can solve the ACID problems, at least for queries using one table. Those logs are contained in the table, so they don't solve the problem of multi-table ACID. And we also solve the problem with reading the metadata because the statistics are kept in the log and we don't need to open file metadata footers each time we want to see what happens inside of the file that will potentially load. Besides of that, the fact that Parquet is immutable and each operation writes new files to the folder, sometimes without dropping the previous ones, gives a few more benefits, like possibility to do time travel or cloning, which is quite interesting concept, but we are not diving deeper into it. But for those interested, I suggest to read a little bit about those two new possibilities that came with open table formats. Let's look at how an open table looks on our storage, how the structure of the folder looks like. Let's start with a data lake table. And as you see, those two examples, table defined as data lake, open table format one, is just a structure of folders. On the bottom, you'll see those part0z Parquet files. Those are most important. Those are the Parquet files that contain the actual data. And besides of those files, we get the data log subfolder with JSON files and Parquet checkpoints. This is the part that describes what's happening in our table, which files are part of which version, the statistics, metadata changes, etc. Everything can be found in the delta log. And on the slide, I'm showing two examples with deletion vectors and without them. And those deletion vectors are quite important concept that speeds up working with our delta lake tables in situations where the changes are quite small. So as you probably all know, when working with Parquet, the optimal file size with the data is most of the time somewhere between 100, 200, maybe 500 megabytes. Like I haven't heard about a situation when an optimal Parquet size were near the kilobytes. That's better for compression, better for processing, but it might be problematic in a workloads where small amount of rows are added, because each small operation requires us to rewrite the whole file. So basically you can have a situation where once a while a small row is added and it requires you to reload hundreds of megabytes of files. To solve these problems, in Delta Lake, we introduced a concept of deletion vectors. So small files that gather all those small changes and just once a while reload them or optimize the Parquet files by adding all those differences, but in bulk. In that case, we don't need to do those whole heavy reloads each time a small change was added. How does work when querying the data? Each time you query our table, you load the data from Parquet files, you load the deletion vectors, and on the fly, you apply the changes each time to the rows that were modified by the operations in the deletion vectors. So as you can see, the insert time and modification time is way faster, but you need to pay for that during the query time when the operation each time has to be reapplied during the query. Looking at the folder structure, quite the same: delta log, main Parquet data files, and at the end a subfolder with additional deletion vectors. Let's look now at the Apache Iceberg. What's important here? Of course, this is a different mechanism, completely different style of how the metadata is stored, but there's something in common. You'll also find all the data in the Parquet files here in the data folder and all the metadata in the metadata folder. So different mechanism, but on a very high level, quite similar. And to end up with Apache Hudi, and also two examples of copy and write. So that would be the equivalent of delta without deletion vectors and merge on read equivalent of delta with deletion vectors. If we look at the structure, we'll see the same high-level idea. Partition data with Parquet files storing the main data, plus Hudi subfolder with all the information about the commits, which are the versions and changes in our table. And now after those 3 slides, you might think that, okay, 3 completely different mechanisms, 3 large books about each of those, but on a high level, this looks quite the same. And that is true. And that is why, besides of those table formats, you can find some mechanisms that or functionalities that try to make them interoperable. By interoperability, I mean possibility to query, for example, delta as it was Iceberg, or Hudi as it was delta, or in any possible direction. We would like to standardize it in a way that no matter in which format you keep the data, other readers could read it as it was the other one. The first idea that was, the first concept that was proposed was delta uniform. That's part of the Delta Lake functionality. This is the functionality that allows you to read delta tables as if they were Iceberg or Hudi tables. How does it work under the hood? You have one folder with data in Parquet files that doesn't change. You have the standard data lake metadata layer, but after each operation, you the mechanism creates a parallel folder with metadata for Hudi and for Iceberg. Only the metadata part is copied, the data is saved only once, and depending on the client that you are using, you can read the metadata sufficient for the client and retrieve the data from your Parquet files. Uniform works only in one direction. Delta needs to be the main format to which you write. You can only read from Iceberg and Hudi. Well, besides of data uniform, we have also Apache Iceberg, which is omnidirectional. That means that still you need to pick one main table format to which you write the data, but it can be any of those three. And you can decide to which of those you would like to also create the metadata. So with Apache Xtable, you can start with Iceberg, read from Hudi Delta or in any other possible direction. But please remember that you always need to have one main format that that allows you to write the data. And there are a few limitations. Not all the functionalities of all the table can be mapped to the others. So this also needs to be kept in mind. Okay, so from the file formats, we've covered file formats, we've covered open table formats, the problems are solved, we are in the Lakehouse. And the last thing we should do is to look at the performance, because the fact that we've moved to open table format doesn't guarantee that everything will be faster, and sometimes we just need to fine-tune the stuff. Okay. Optimization techniques in open table format. In most of the cases, we want to achieve something that's presented on this slide. So our data is saved in those Parquet files at the bottom. No matter what technology you're using at the bottom, those are Parquet files. And those Parquet files have some ranges of possible data you can find there that may overlap. Each time we query the data, we try to skip as much of the Parquet files possible if we know that nothing that we require can be found there, and pull the minimum that's required for our query. To make this more efficient, we would like to optimize the layout of the files. For example, make them detached or isolated or not overlapping, as you can see on the screen on the right. And also have proper statistics that will allow us easily and quickly find which Parquet formats potentially are needed in our query. The first technique, the one that was known even before the open table formats were proposed, is partitioning. Partitioning is quite a simple idea that assumes that we prepare a folder structure based on the unique keys of the dimensions that we assume might be used in our queries. And in this folder structure, we save our Parquet files, but filtered to only those keys that we have in our folder names. Yes, so for example, if we partition data by country, as it's on the first example, we'll have a folder structure like country Austria, country Brazil, country Chile. All the files inside will contain only those keys that are found in the folder name, and the engines querying the data will know that if the predicate uses those columns, then the folder structure can be used to easily skip the data. In many cases, when we know the data skew, and we know our queries, this might be completely enough, and this mechanism can work extremely well. But there are situations where it's not perfect. For example, in situations with a huge data skew, or in situations where we would like to use multiple columns and those subfolder structures won't allow us to benefit from the partitioning. Okay, so yeah, I've talked a little bit about this slide before, so to say it one more time, with partitioning we can hit those challenges that are described here. If we pick too many folders or too many columns and create deep folder structures, we can over-partition the table, at the end having lots of small Parquet files, which is not effective. We can have a problem with uneven distribution of the data. and some of the files will be extremely small, some extremely big. We don't have any possibility to somehow smooth this. This is purely based on the partition keys. And yeah, and we are fully dependent on the cardinality. So no way here to enforce the file sizes, to combine the keys, etc. Pure partitioning will not handle that. So what's the next possible solution? Z-ordering. Z-ordering assumes that instead of basing only on the uniqueness of keys on the columns, we pick the partitioning columns and we try to order the data using, for example, the Z-curve, which is one of the possible ways of ordering multi-dimensional data. And based on the order that's defined by the Z-order curve, we split the data into buckets of a similar size. For example, by a million of rows. This mechanism solves the problem of uneven distribution and the dependency on the cardinality of the columns. Z-order might be effective even on continuous columns, and we don't need to care to pick something with low to mid cardinality. Integer values like salaries or unique amounts are also okay for this mechanism. Z-order still have few limitations and challenges. The first one is Z-order is stateless. So after applying it to a table, we don't modify the metadata of the table in any way. Also, the way we split the files is based only on the number of the rows. So the mechanism doesn't check effectively what's the size of the files. And in some edge cases, we can still have quite uneven distribution of the volume between the files. And also Z-order is quite hard when considering incremental loads. It is possible to combine Z-order with partitioning and somehow limit this challenge by just reclustering, for example, the hot data at the end of the table, but still it might be a little bit problematic, and incremental loads, solving incremental loads and rebuilds of the our structure might not be perfect. Yes. So what I've also already said, in Z-order we load the files. Sorry, we split the files by evenly balanced buckets of rows. It aims to be incremental, but it's not always perfect. And it also brings this important feature that's called locality preserving, which means that, as you see, the things that are near on the curve should be also near in the multi-dimensional space. Intuitively, you should see that those areas here are like a cluster of data quite similar to each other. It's not perfect. There are those long jumps you can see through the whole table at the middle, the horizontal one, but still better than the curve created by the partition data that we sometimes call a snake curve. Okay, so Z-order, good step forward, but still not perfect. And the last technique we'd like to show is liquid clustering, related with Delta Lake. And this technique was created to solve the problems and challenges related to Z-order. The first thing, liquid clustering is stateful. So the columns used for clustering are can be found in the Delta Lake log in the metadata. So you'll know how the table is clustered by. Then, at least at the beginning, liquid clustering used a different curve, not the Z-order one, but the Hilbert curve that is optimal, let's say, or at least better performing than the Z-curve in in case of locality preserving. And the last thing that's also important is that in liquid clustering, the mechanism is not looking only at the number of rows, but also at the potential size of the file. So it's trying to split the files a little bit smarter, not just assuming that the rows are quite similar, and this row count based split is good enough. I don't have a demo here, but just to close this topic on optimization, I'd like to show one generated edge case. On the right, you'll see the distribution on the table. This is just generated table with uniform distribution of rows. So they are evenly distributed across whole this scope from 0 to 50 on both columns. But what's modified here is that on the top left half, you will see the rows named light. They have just 4 columns with integer values, small rows. And in the heavy part, besides of those 4 rows, we have added few string columns with long comments. So the distribution, when you look at the row count, is uniform, but the volume is heavily skewed to bottom right. And now, if we look at the diagrams on the left, you'll see how Z order on the left worked compared to the liquid clustering. So in the Z order, you can see that those files are quite similar in size if we look at the blocks on the table, but the volume on the bar chart is quite different. The first 6 are those files that cover only the light part. With liquid clustering, the mechanism was based more on the volume, and that's why it squeezed the files towards bottom right and tried to prepare something that's more regular when looking at the volume. And this is one of the mechanisms implemented in liquid clustering that is solving a problem we sometimes hit when using Z order. To finish this section, I'll just say that I wouldn't say which one. None of those. I wouldn't say that the liquid clustering is better in 100% of the situations. So if you'd like to use one of those two, always check your own data, run a few queries, and see what's performing better, what's faster, what's more effective, because might be that is not liquid clustering, and still Z order with partitioning in your specific use case performs better. So yeah, that'll end up the optimization part. And now to end, we'll switch to Marek's screen to see some demos. So Marek, screen is yours.
Thank you, Tomasz. Let me just share my screen to show you some real example. So, what is the purpose of the demo, and what I would like you to demonstrate here? So we already discussed that there are a few parameters and few ways of laying out our files for analytical purposes. And I would like to show you on a real example what is the impact of the file layout. So whether it really matters how you structure your data from totally unsorted going through some ordering, ending up with some more sophisticated methods like Z order, like Tomasz mentioned. We have a couple of parameters that we can play with to also further impact the way the data are filtering out during the scan. In particular, the row group size seems to be of great importance. And the question is whether the default row size, which is 128 megabytes, is really optimal in all the cases. As a spoiler, I will show you that it's not. And I will also show you, based on some metrics and statistics, how you can really troubleshoot and analyze the impact of your both file layout, row group size, and file size, and how all these three things all together may result in reduction of the number of processing of unnecessary rows that should be filtered out thanks to the methods that we discuss in the Parquet session. So for the demonstration purposes, we used very popular TLC trip record dataset. So it's a set of data sets related to New York taxi system. We will use Python APIs for these purposes to make things easier. So we start out with creating our brand new virtual environment. There is no magic here. As a compute engines, we will use here Apache Spark, which is in fact one of the most popular query engines that you may come across in your day-to-day analytic jobs. Then we need to download our data set to make some meaningful amount of data for demonstrating some of the features. Once we got this all together, we'll start PySpark session. We will work on tables powered by Apache Iceberg table format. This is why we need to add additional package that is responsible for handling that type of tables. We also set a couple of Iceberg-related parameters, and we will run it, of course, on our local machine using 8 gigs of memory. Spark session initialization, that's default stuff. We will prepare some temporary structure just to read the data. By the way, we download the data in a Parquet format to avoid any conversion between CSV and for making the loading process quicker. So what we would like to achieve in this step, we would like to load this downloaded files into our one table. And here we got a couple of parameters that we would like to verify the impact of. So first of all, we would like to verify a different set of both table layouts and parameter values. So we will start with a base layout, meaning that we do not put any order of the data. We just load them at random without imposing any sorting. So these are denoted with the base prefix. We will verify the impact of just basic sorting using a few columns. And finally, we will also compare that with this z-order table layout. Apart from that, we are going to analyze the impact of two parameters. One is the default target file size. This parameter controls the size of a single Parquet file when using Apache Iceberg with Parquet as a file format. And the other one is the row group size. By default, it's as I said, 128. But we will also verify whether decreasing that to 4 megabytes may bring additional benefits while doing scans and filtering out unnecessary words. In order to also demonstrate file pruning or file skipping mechanism, we would like to show you how it would work with the file size of 16 megabytes instead of 512 megabytes. But please be aware that decreasing the file size is not recommended in most of the use cases when you have a large-scale data set. But here, since our data set is not that big, and we would like to demonstrate the mechanism of and the impact of file skipping, we decided to artificially decrease it to 60 megabytes just to demonstrate some of the features. We also have two sample data SQL queries that will filter out based on some IDs, and also additionally the query number 2 filtering out using total amount column. And here it comes, if you analyze it closer, some steps that will create the partition table, this base one, and also the one that have some additional parameters set to decrease the row group size or file size. But for now, we don't impose any layout. We just load it as it is. And now, once we got this setup prepared for some of the tables, we are going to impose either sort or the order based on two columns, so two ID columns. And we, of course, need to run it over tables that we would like to change the layout to. I will scroll down just to the results of the further queries, because once we got this restructured, we run a set of queries, so actually it's two of them, and then compare the results. So what we got here? So we got like our test cases. We got a number of, I will just like discuss the most important columns. So the test cases, the output rows, meaning how good we are at filtering out at one doing the scan. So in other words, how many files were transferred downstream to the query engine. We got, of course, the time needed to process the query and also some standard deviation. So what we got here, so for the base, what we observe here, so for the tables that were simply loaded without imposing any order, and with most of the cases with different file size. When running these queries, we don't observe any output rows filtering. So meaning that we are reading all the files, all the rows, and all the rows are sent down the road, and the query engines need to later on process them. But when we start imposing some orders, we are seeing that, for example, for just very simple sort mechanism, we already experienced reduction in the output rows, meaning that our row group pruning mechanisms work. Because we didn't change the default size of the file, we didn't observe any file skipping mechanism, because actually our data set was not, in our case, was not possible to skip the whole file. But for example, if we decrease also our file size to 16 megabytes instead of 512, we observe an enormous file skipping mechanism, and in combination with the decreased row group size, we observe the best performance over here, because we got both reduction of the number of rows processed from like 10 times, from 50 million to 4, so even more than 10 times. And also lots of the files were skipped, and this results in the lowest number of megabytes read from the underlying storage system. When compared to the order, we see that this the order in the similar configuration also perform very well, also resulted in output rows reduction and file skip. But in this particular use case, it turns out that simple sorting with decreasing the row group size proved to be the optimal way of structuring your data. And this is something that Tomek already mentioned, that in many cases it can be really use case specific. But what about the other query? So the one that was marked as Q2. Here we, of course, did a very similar setup of changing the layout and then running the query. And here we also compare the base results. We have like a default target file size and default group size of 128. And here again, we didn't get any additional benefits from the row group pruning or files pruning because all the files were read and no files were skipped, and actually no rows were pruned during the scanning mechanism. The same table with decreased row group size and decreased file size, and here we got a great reduction of the megabytes read. So we most of the files were skipped, most of the rows were also pruned, and this is why this combination of parameters proved to be extremely efficient, decreasing the query time more than 7 times, and also decreasing the number of megabytes read by more than 3 times. In this example, sorting was a bit worse, but still very close. So we can conclude that in many cases, in order to get really a decent performance, it's not only about like turning some mechanism like the order of sort, but it's also about smartly way of assessing the optimal group and file size in order to benefit the most from these sophisticated mechanisms. And the other conclusion is that your setup might be very dependent on the query types, query specifics, and also dataset specific. So you cannot say that that either of these methods is globally the best. But in fact, using one of these ordering mechanisms really brings a lot of benefits to optimizing the scan performance. Thank you. So I think we are done with both the theoretical and practical part, and now it's time for Q&A.